Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, watch some baseball in the background. Let's look at domain, range, and end behavior, kind of introducing them in a way. I'll talk about what they are in a bit of a brief format, but I really want to get to the problems. I got 15 practice problems to look at, some set and interval notation, a couple things with just exploring the graphs with them as well, and some situations with word problems. Without further ado, guys, I'm going to hang around in this corner right here, and let's get started. All right, so for the first four problems here, we're going to be either doing interval and or set notation with information provided or number line graphs, things like that. Number one, write the interval shown on the number line as an inequality using set notation and using interval notation. Now, set notation is kind of writing out inequalities, if you will. The entire notation uses some other verbiage stuff, which I shouldn't say I should ignore because it is truly set notation. But set notation uses these curly braces here, and what we have to do is, you can tell there's no variable defined here. And our solution set has to reference everything that we see here from 5 onward. 5 is included, and onward greater than. But if I defined all of these as some variable x, I could say that my set of solutions is x, is some x, such that that x is greater than or equal to 5. Now, for my students' sake, I'm really highlighting and focusing just on this part right here. The x is greater than or equal to 5. Yeah, you can call it inequality notation, what have you, but I really just want to make sure that they understand how they're going to be referencing things, especially if they already knew that an x was there or if it was implied. And for all intents and purposes, guys, I'm always going to be using the variable x. But I will write them out in full set notation if you'd like. Anyway, that is set notation right there. Okay. Interval notation, on the other hand, uses kind of something a little different here. What it does is it talks about the upper and lower, I should say lower first, the lower and upper bounds, not assuming a variable x, and just talks about how far left does it go, how far right does it go, if you're looking at, say, a number line right here. Or in the y sense, when we start looking at y variable as well, how low does it go, how high does it go. Now, this goes as low as 5, and it includes 5. So what we do for interval notation, guys, is we use a square bracket when we're referring to including our bound value. We will use a parenthesis when we are not including our bound value, when you would see like an open circle, for example. But here was a closed circle. 5 is included. 5 is the lower bound. And I'm going to put a comma. So lower bound here, comma, upper bound here. Now this goes on forever to the right. It goes toward positive infinity. So is there an upper bound to speak of? Not really as a value, but we will still put infinity. And the infinity symbol is this sideways guy right here. Now you're going to see me put negative infinity at times when we talk about going this way. So here I'm just going to put the positive infinity, and I'm going to tend to make sure to always do that. Now we have to close this with either a square bracket or a parenthesis. Now which one should we do? Well, guys, infinity is not an actual number. It's something that actually can't be reached. And if a square bracket has to do with including the value, infinity is not a value. We do not include it as we can never actually reach it. It is more of a concept to represent a boundless entity, if you will. So we're going to put a closed parenthesis, we're going to close with a parenthesis right there. So that's that answer for interval notation, and set notation is right here. And like I said, for my kiddos, I'm just really focused on the inequality portion, but the rest of it defining x, such as blah, blah, blah. I'll keep looking at that. Okay, there's number one, and I can kind of speed up a little more now that I talk about that, and you'll see some diversity in these problems, including compound inequalities, more with parentheses and square brackets and such and such. All right, number two, write the interval 5, 100 as an inequality and using set notation. I mean, for me, it's kind of going to be both-ish, if you will. I hope that's okay. Now, before I do that, let's translate this as a number line. Let's see what this would actually look like here if you really want this tie-in of, I don't know how to go straight from one to the other. Maybe you do, maybe you don't. But I know how to graph it first, and maybe I can go from there. Excuse me. So if 0 was right here, and 5 was right here, and 100 was right there, the 5 with the parenthesis means 5 is not included. That's where you would put, say, an open circle. And 100 is included because the square bracket is there. That means closed circle right there. And they're not asking us to graph it as a number line, but this is going to be my transition for you for this problem. So what we're looking at, guys, we're looking at between 5 and 100 are all of our x's. So if we're going to use set notation here, we say it's defined for all x's such that those x's are between 5 and 100. Now a compound inequality looks like this, between 5 and 100. And I'm still missing something, I know that. So again, for my kiddos, I'm really looking at just that portion there. So x is between 5 and 100. 5 is less than x, which is less than 100. All your solutions fall in between there. Now 5 is not included. That's why we said just less than and not less than or equal to. But 100 is included, so we will put less than or equal to there. So x is between 5 and 100. 100 is inclusive. And that's your answer. That's the set notation. That's as an inequality. And there's whole set notation again. Kind of, there's so many particular things in math that I sometimes like to call them out for being a little too nerdy, a little too formal. And this can be one of those situations. I get why they do it, but let's assume an x is already there. Let's imply that the x variable is already being used just for the sake of consistency. Number 3, write the interval x is between negative 25 and 30, negative 25 included, using set notation and interval notation. This is where it can get tricky because this is where I tell my kids that this is set notation right here. And it kind of is, but if you actually truly wanted to do set notation, I would now use this part right here. It's all x's such that x is between negative 25 and 30. So there we go. That's official set notation, but for my kiddos, my set notation version is just that. That is totally okay. I should stop talking about my kiddos and talk about anyone else who's probably watching this. Interval notation is now where, I'm not going to do another number line. We go from negative 25 to 30. Negative 25 the lower bound, 30 the upper bound. Negative 25 is included, so we use square bracket to open up with. 30 is not included, so we use parenthesis to close. Now, it's very possible, guys, that we are going to, in fact, we're going to run into it here, but it's possible that you're going to run into ones that are not included for both. So if you get parentheses on both, don't confuse it for an ordered pair. That's something completely different. This is what interval notation appears as. So number 4, this is set notation, and we're going to write it in interval notation. X is between negative 3 and 5, both exclusive. They are not included in this when we talk about interval notation. So interval notation here from negative 3 to 5, neither are included, so I'm going to use parentheses around that. And no, that is not an ordered pair. That is not an ordered pair. That is just simply from negative 3 to 5. If you take calculus, guys, you're going to see interval notation a lot. You're going to use it for ranges for increasing to decreasing functions, points of concavity, things like that. It's just a quicker set to be referencing what it is that you're talking about, spanning on x. And because it's almost always x that you're referring to in those situations, well, that would be something to talk about. And then domain and range, same thing. Domain is always for your input for x, range is always for y or f of x or whatever they call it. So it's very just common to just use that because the inequality stuff almost just gets in the way. You really don't need all that excess information. So there's a point and need to it. I just want to make sure you're well aware of that. Okay, write the domain and the range of the function as an inequality using set notation and using interval notation. Also describe the end behavior of the function or explain why there is no end behavior. So I haven't gotten to that last part yet, and I will. Let's start with, and you've noticed I've probably been using blue for set notation, so I'll start with that. So the graph of the quadratic function f of x equals x squared plus 2 is shown. So they graph it for us. No need to kind of graph it on your own. Here it is. We're looking at this graph, and we're going to ask ourselves, guys, with domain referencing x values and range referencing the y values, how far left and right does this graph actually go? And because the arrows point this way, and don't just think that means up, it also means up and right and up and left, then it is going forever right. And it is going forever left. Despite the fact that it's also going up and very sharply, it is going right and left forever. Our domain can be written in several ways with set notation, guys. We can use from negative to positive infinity, like this. Now remember, the infinities are not included, so we're going to write it like that. There's another form that looks like this. I'm trying to remember the actual, and this is bad for me as a math teacher to say, I can't remember. But there's a symbol right here. It's like an E. And then this one right here. I don't know if I'm doing this perfectly because I'm kind of thinking about it on the fly. But this is saying the set of all x such that x is, I don't know. is the set of, I can't remember, but this is all real numbers. All real numbers. For my kiddos, if you just put all real numbers, dude, I am so fine with that. All real numbers. If you wrote out all real numbers, I'm good as well. Otherwise, that negative to positive infinity, but you're going to see that as well in interval notation when I get to it. The range is a little different story. If domain is referencing how far left and right we go, and this thing goes forever, range is about how far up and down we go. Now, as I mentioned, this graph does go up forever, so there is no limit on how high we go up, but it does have a vertex right here where it actually bottoms out. There's a lowest point on this graph that we do hit. There's a lowest point on this one, and this one's at the y value of 2, and it includes 2. 2 is actually a part of it. So for the range here, I can say it's the set of all y values such that y is greater than or equal to 2. What that's saying is y can be any value 2 or greater inside this graph. Those are all your functional values for it. So that's the range of this thing, and the domain is all real numbers. It goes forever left and right, and this thing goes forever up, but it just goes as far down as 2. And that is set notation. Interval notation here for the same thing would have looked like going from negative to positive infinity, non-inclusive, that's why I use parentheses and not square brackets. The range goes from 2 to infinity, to positive infinity. So you might notice that here we don't write it as a compound inequality to say y is between 2 and positive infinity, because it's really not necessary when you have a variable to compare to a boundary point. Here you don't have a variable and you must list left and right bounds. So we go from 2 as a lowest bound to positive infinity as a highest bound, and that's just our way of putting it. For interval notation, guys, we're not going to say all real numbers. We are just going to say left, right bound as the infinities, and go. So there's the domain and range version of that thing. End behavior. Let me actually underline these first here, just so you know, because I'll keep doing that. All right, end behavior. End behavior, let's use purple. End behavior asks us, when we go forever in the x direction, in the positive x direction, what are the y values doing? What's their behavior? And as we go forever to the left in the x direction, what are the y values doing? So as we go forever right, we see these values going forever up. I'm looking at the graph right here. As it goes forever right, it's going forever up. In the long run, ultimately, in the long term, that's what the y values are doing, despite the fact that it had a point where it got low and did stuff like that. As it continues forever, it goes up. So our notation for this looks like this. As x approaches positive infinity, y approaches positive infinity. This is a way of saying as x goes forever right, y goes forever up. As we see the x values that are way off in the future distance, you're going to see y values that are, well, you're not going to see them. They're so high up that they're gone. And that's what we're saying for end behavior going to the right. Going to the left, we actually see the same behavior, but going the other direction. As x goes forever left toward negative infinity, y is also still going forever up toward positive infinity. So we're understanding the end behavior of this thing, where it came from, kind of. That's like looking in the past. So long ago, we were a peak of a civilization before we bottomed out at 2 with Adam and Eve. All right, so as x goes forever left, y still, yet again, goes forever up. That is the end behavior notation. That's how we write it. That's how we talk about it. And if you want to say it out loud to kind of make sense of it first and then figure out the notation later, great. As long as you can interpret the graph alongside it. And there it is. All right, now we've seen one of those. Let's see how number 6 works. And this is y equals 3 to the x power. Now, my class is an integrated math 2 class, which means in integrated math 1, they did see exponential functions. To what extent? Not a great one. It was part of distance learning. I don't know how far in the future, if people are watching this in 2040. In 2020, we had COVID. In 2021. So f of x equals 3 to the x power. In an exponential function, what happens is it does take off on one side. I'm not going to say parabolically, but it has a curve aspect to it, and it kind of sharpens as you go. But the other side, there's no vertex. What happens is it diminishes closer and closer, and it gets closer towards 0. But it never actually hits 0. It has to do with negative exponents and things like that. Even if you can look closely enough, you even see kind of a gray dotted line here. I'm going to sharpen it up by giving it a nice red dotted line here. This is what's called an asymptote. I'm going to spell that. This is what's called an asymptote. And it's a visual feature that allows you as the viewer, like myself, to understand that our graph is actually never touching this line. It gets closer and converges toward it, but never actually passes it. And that's what exponential functions do. So let's go ahead, guys. Let's take a peek at the set notation, interval notation, and end behavior of these things. And they do kind of relate when you see some of them. Now, there are a lot of times, guys, you're going to see the domain just be all real numbers. And that's the case once again right here. I'm just going to go and give the all real number symbol. I hope you're kind of okay with that. It's going to be similar to that guy. Oh, they do want set notation. Let's actually add the rest of the stuff. I think this is how you write it. It sounds so bad for me as a math teacher to say it. It's probably even worse that I didn't research it beforehand. If you know me with my videos, I like to enter them kind of blind. I haven't really seen these problems. Like, I haven't practiced the problems beforehand, so let's always hope I can do them correctly. Now, the range is a different story, guys. If you consider the points, they do go up forever. And, of course, they don't go down forever. But unlike this one, which actually hit the point of 2 for y, this one never actually hits 0. That's the point of the asymptote, the exponential function. This range is limited to only positive numbers. Even 0 doesn't count, but it gets super close to 0. It gets as close to 0 as it can ever get, 0.00000000001. You know, it goes super low. Now, do not put this would be incorrect, some y is greater than or equal to 1. No, I mean it is, but also what about the numbers between 0 and 1? Those should also count. So our way of putting that is just y is greater than 0. It's not equal to 0, but it is greater than 0. So our range here, we're going to say y is greater than 0. That would be the equivalent of that one there. Now again, for my kiddos, you can just put the all real number symbol, y is greater than 0 and stuff. My point for you guys when you're doing it is just to feel it out, not to write out the full notation. I'm not going to be too picky with that. Some things I will be. This is not one of them. Now, domain and range for interval notation. Domain here is once again all real numbers, but we have to now state from negative to positive infinity. You know what I'm going to do next time for these is I'm going to either write out all real numbers or I'm going to say the negative to positive infinity. And range here, y is greater than 0. So 0 is not included, but it is the lowest bound. Positive infinity, of course, is never included, and it is the upper bound there. So there's the domain and range. All right, let's look at the end behavior of these ones here. As x approaches positive infinity. Oh my gosh, where's my infinity symbol, y'all? As x approaches positive infinity, as we go forever right, once again, we're seeing the y values go forever up. This is where we find them. Whee! Y goes forever up. It increases without bound is my way of saying that. Now, as x goes forever left, you have to be careful here because some people might think that y is going down forever, and it is technically going down forever. As you go further left, y is going closer and closer, but it's not going down forever. It's not hitting all the negative values. It's not getting toward negative infinity. It's getting towards 0. Does it ever equal 0? No. But it approaches it. It converges toward it. And that's why we say that y approaches or converges toward 0. Actually, that number. It never equals it. And that's why we're using arrows and not equal signs. It's not as x equals positive infinity. It's as x approaches it, as it gets closer, as we draw an arrow to it. You can't see what I'm writing. I just totally realized that. I always forget when my picture's in the way and I say all that stuff. So, my bad, but there it is. All right, guys. So there's that first page stuff. I think numbers, well, let's see what comes next. But I think it's more of the same. So domain and range, end behavior, set and interval notation. So let's move forward. Yes, indeed. Numbers 7 and 8, and then we do some other stuff. Okay, number 7 and 8, another graph is shown. This is y equals 2x minus 2, so a slope of 2 and a y-intercept of negative 2. We're doing the same stuff, domain range. Now, this thing does go forever left and right. The arrows indicate that there's no stopping point for this one. So as I promised here, this time I will say I'll go from negative to positive infinity on x, just giving you some versatility so you can practice every which one. Y does the same thing though, right? It goes forever up and down. So once again, there's an all real number sense to this one as well. And teachers or websites or whatever, tests and stuff, they can play with a bunch of different graphs, like this one looks a little different. But when it comes to equations, there are only so many ways that you can actually limit your domain, and range is really based on the nature of the function. Linear functions, they do go forever left and right. They do go forever up and down. as long as we're not talking about a completely vertical or completely horizontal line. So there's no way of stopping that. But if, you know, I don't know. So I'm just going to say you're going to see a lot of that. You're going to see a lot of that. And so same thing for interval notation, I should say. Negative to positive infinity and negative to positive infinity. All real numbers, if you will. End behavior says as we go forever to the right, which way are we going? Forever up. As x increases without bound, y increases without bound. As x decreases without bound, this is an instance, I got to get better at those infinity symbols. Y is going down forever this time, like toward negative infinity there. So right and up, left and down. You know, so there we go. Now as the last one here, we have a semicircle and closed circles at the end, which means those points are actually included, the point negative 4, 0 and 4, 0. So domain, does this graph go forever left? No, it only goes as far left as negative 4, and it goes far right as positive 4. So the domain is restricted from negative 4 to 4. Now every point in between counts, right? It hits negative 1 and it hits 2 and it hits all those values there. So x goes from negative 4 to positive 4, including those two. So in set notation, that looks like the set of x's such that x is between negative 4 and positive 4 inclusive. Whoops. And then the range, we ask how low and high do the points go. So the lowest points you'll see are on the x-axis. That's y equals 0. And then you can see that the highest points, it goes as high as 1, 2, 3, 4. And it hits 4 up there. It includes it. So it goes between 0 to 4 right there as far as range goes. And I know people have trouble seeing that sometimes because you think about the y-axis only. No, it's all the y values that exist. There's a y equals 3 that exists right here and here. You know, things like that. But it goes from 0 to 4. From 0 to 4. And it includes them. That's what the whole closed circle things are all about. 0 to 4. All right? So the interval notation will be square brackets this time from negative 4 to positive 4. And then the range is from 0 to 4, like that. Now, end behavior. Although these graphs end behavior is more like long-term behavior. So let me go and read what they said about conditionally if they don't explain why there is no end behavior. That's what I believe I want to talk about here. Like there's no, it's not, as x approaches positive infinity, I mean, when x is 5, there, you know, that's out of our domain. So there's nothing really to say with regarding that. Why is there no end behavior? Because there is no long-term effect. So right now I'm just going to say, guys, no end behavior. I'm not going to really, oh my gosh, I'm not going to get much deeper than that on that one. Okay. All right. Now, there are other graphs that can, sorry if you couldn't see that, my bad. Now, there are other graphs that could feature no end behavior. I'm not sure if this is a particular good time to really talk about them, but if you had like a sine wave or something that just goes up and down forever like that, I mean, it oscillates between, say, negative 1 and positive 1 or whatever, but there's no, the end behavior oscillates. It doesn't approach a single value. It kind of, it oscillates. It bounces around. So there are different ways to have no end behavior kind of like that, at least not to speak on it really clearly like this. So anyway, just letting you know. Okay. Numbers 9 and 10. For the given function and domain, draw the graph and identify the range using the same notation as the given domain. So this one, the notation they use is interval notation, so I'll be using that here. And this one's using set notation, so I'll be using that here. Now, what's really interesting, and I kind of hinted at it before, is if you have an equation, you could actually identify what the domain is based on certain things. But the range is almost always better understood if you see its graph. So it is best that we do draw a graph for it. So I'm glad the book asks us to. So this is in y equals mx plus b form. We got a slope of -1 and a y-intercept of 5. So starting at 0, 5, we're going to go down 1, right 1, over and over, and draw that graph. Now, I'm going beyond what the domain is limited to. I'll let you know right off the bat right now that I'm going beyond that. I'm just giving you the idea of the graph first so you can know, I don't know what to do in the future. But here's what the original graph would look like. Now, what we're going to do in a second, guys, is we're about to limit this domain from -3 to +2, and we include -3 and +2. That means instead of drawing the graph in full like this, what we really want is just a graph that goes as far left as -3, which means this is our stopping point, and +2, which means this is our other stopping point. That's our lower bound and upper bound. And I know that sounds weird because domain lower bound as in left bound and right bound. So we're only going to go just that far. So let's get rid of everything else but that right there. And there really theoretically shouldn't be an arrow. Let's take out. There we go. All right, so that's what this graph is going to look like now that we've, I don't know, patched it up. Okay, so now identify the range. How low and how high does this graph go? And let's use interval notation for it. It goes as low as, remember, this is y values. It goes as low as 3, and it goes as high as 8. So our range goes from 3 to 8, and it includes those points as well. All right, and that's your graph. That's your graph right there, and your range. Okay, next one. Y equals 3/2 x plus 1. Let's draw that graph, and this time I'll stop it when it kind of wants me to stop, but let's start at 1 as a y-intercept right here, and then let's rise 1, 2, 3, and run 1, 2 like that. Can't really fit any more there, so let's go the other way. Fall 1, 2, 3, and run 1, 2. Now you might notice here that the domain is clipped at, I shouldn't go any further left than -2 because the x value should only be greater than -2. So -2 is my left bound. But also remember, it just says greater than. It doesn't say greater than or equal to. So what we have to do is draw an open circle on -2 because it's not included. It's not included. But everything greater than it is. So I'm going to draw an arrow on the other end of this thing as I continue it through. And it does go forever to the right and forever upward. So the range on this one is in set notation, it's the set of all y values such that y is greater than, looks like -2. Look, even the -2 right here is also the limit on the range. It's everything greater than, and then we're set from there. And there it is. Assuming I did the graph correctly, which I believe I did. Okay, guys, I'm going to run into the final 5 problems. I don't know if they all are, but I think they're all situational kinds of things, or at least they have some words in it. Write a function that models, determine the domain and range, graph the function using that domain. Oh, sorry. I determine the domain, graph the function, and identify the range. One more time, they are mentioning that, domain can be identified kind of early on based on the situation or equation. Range is better identified when you actually have the graph provided. Okay, a bicyclist travels at a constant speed of 12 miles an hour for a total of 45 minutes. Use set notation for the domain and range. So the domain is spoken of right here for a total of 45 minutes. That means this is our upper bound. 45 is our upper bound. Now, in a real world situation, the bicyclist traveled for all 45 minutes. We're not going to assume negative time is used. Time 0 is when the bicyclist began bicycling. So what we're going to say for the domain here is his lower bound is 0, but his upper bound is 45. This is as far as time t. And this time they're using a lowercase d as our y for distance and a lowercase t as our time for this thing right here. Oh, they used hours. This is just fantastic, guys. I'm sorry about that. I didn't notice that. So 45 minutes out of 60 minutes for an hour is 3/4 of an hour. That's 0.75. Let me do that one more time for you. 0.75. I really wish that this is the book being the book. Okay, now I want to draw this graph next to figure out what the range is based on that information, because I got to use this 12 miles an hour concept. So traveled 0 miles at 0 hours to begin with. This is a starting point, and eventually reaches, this is fantastic, 12 miles after a single hour. So 12 miles would be 10, 11, 12 would be up here. Fantastic that they're doing this. I could find some points in between though, right? If you go at a constant rate of 12 miles for 1 hour, then after a half hour, we can take half of 12. So that's going to be 6 miles after half of an hour. So I'll get that point in there for you. And I think I'll be comfortable with just those ones. Now we're limited in our domain up to the hour. Up to the hour there. No, I'm sorry, not up to the hour. That's actually part of the point. That's probably why they're saying this, because we don't get that far, right? We only get to 45 minutes, so we only get to that 0.75, which is, this problem, guys. This problem. 0.75 is right here. This is 0.6, 0.7, 0.8. So 0.75 is this guy right there, and that's why it's good to kind of have that graph with it. There we go. So that's our domain. Going to just that guy right there. Now that's at 9, and if you're questioning whether or not it's exact, I can tell you right now that it is exact. That is where it's going to land there. So our range, oh, I'm sorry, they want set notation, don't they? Not interval notation. Set notation would look like the t values such that t is between 0 and 0.75, because this is represented in hours. And the range are all the d values such that d is between 0 miles and 9 miles right there. And that was kind of discovered after drawing it with the situation at hand. So there you go, set notation. Okay, I have to kind of remember those things because I can forget. I'm a little rusty. All right, number 12. An elevator in a building, tall building, starts at a floor of the building that is 90 meters above the ground. The elevator descends 2 meters every half a second for 6 total seconds. Use an inequality for the domain and range of the function. Okay, this is what I tend to call set notation to my kiddos, just use an inequality. So domain, it lasts for 6 seconds here. So we go from 0 to 6 on t. Like that. Now I want to draw this graph to figure out where it ends up first to figure out the range here. Okay, so we start 90 meters above the ground at 0 seconds in, and then we lose 2 meters every half a second. So half a second is right here. If I lose 2 meters after that, oh, this is fun, huh? If I lose 2 meters after half a second, that's 4 meters after a single second. That's kind of hard to put in 86 there. So what I'm going to do is I'm just going to take away 4 seconds every time until I hit a factor of 10, like one of these numbers here. So 86 after 1 second, 82 after 2 seconds, 78 after 3 seconds, 74 after 4 seconds, 70 after 5 seconds. So after 5 seconds, it hits 70 meters here because it's 2 meters every half a second. So at 6 seconds, it's another 4 meters after that. So that's 66 right there. That is 6, 66. Very satanic. Remember, that is an actual ordered pair there. So that's kind of as best as I could do. Maybe they want us to make a table. I don't actually know. But ultimately, drawing the graph there kind of still gets me what I'm looking for there. So there's the graph that represents that guy. So the range is going from, remember, you do the lower bound first. 66 is the lowest part. So 66 here, and then H is the height, and it goes up to 90. So there's my domain and range for that one. Is that all they wanted? Draw the graph. I did. Yeah. Okay. So there we go. All right. HOT, higher order thinking, focus on it. Explain the error. Here we go. Cameron sells tickets at a movie theater. On Friday night, she worked from 4 p.m. to 10 p.m. and sold about 25 tickets every hour. Cameron says that the number of tickets n she has sold at any time t in hours can be modeled by the function n of t equals 25t. So 25 tickets an hour, where the domain is 0 to 1 in t and the range is 0 to 25. Is Cameron's function along with the domain and range correct? So she sells 25 tickets every hour, and if n is the number of tickets she sells at any time, then the function seems to make sense. The function seems to hold up because after 1 hour, she would have sold 25 tickets. After 2 hours, 50 tickets, etc. That one looks pretty good right there. Now, the domain is 0 to 1. And I'd say the problem with that is if t represents the number of hours, she goes from 4 p.m. to 10 p.m. That's a 6-hour span. That's 6 hours. So it looks like her domain should go from 0 to 6. Some people might argue it should go from 4 to 10, and there's kind of nothing wrong with that as well, unless you just want t to have a starting value of 0, just, time 0 is where you begin. So hour 0 is 4 p.m. to us. So it should go 0 to 6. That's kind of, I'm not going to write anything else, but the range, the domain is the incorrect part. And you know what? And that actually affects the range as well. Actually, what is the end range? Does she only sell 25 tickets after the 6 hours? Well, no. If you take n of 6, that should give you 25 times 6, which means that's a total of 150 tickets after 6 hours. So her range should go from 0 tickets sold to 150 right there. So the domain and range are the problems there, and we have addressed them. The variables are good, and we're taken care of. 2 more questions to go, guys. Here we go. The graph of the cubic function f of x equals x cubed is shown. What are the domain, range, and end behavior of the function? Write as an inequality using set notation and interval notation. Now, I noticed earlier that they actually want the inequality and set notation. I'm just going to do set because it has the inequality in it. Set notation and interval notation. So this graph here, although it has a little flattening out here, it plateaus. That's what cubic functions will do, at least basic ones. It does go down forever at one point. It does go up forever at one point. And of course, as you see here, it does seem to go left and right forever. So the domain and range are both all real numbers. They're both all real numbers there. They go from negative to positive infinity. Actually, you know, for the sake of time and convenience and all that stuff, I'll just go ahead and say domain, all real numbers, range, all real numbers. I want my kiddos to know they can say that. And then the domain here, let's go from negative to positive infinity. And the range also, negative to positive infinity. Fantastic. All right. That's A. B. How is the range of the function affected if the domain is restricted to negative 4 to 4, from negative 4 to positive 4? Right? The range is in So now we're just going from negative 4 to positive 4. Looking at this graph here, it would now clip off everything here. We ignore all that, and it only hits it from that point up to that point right there. Now, as a graph, that's really hard to look at and say you know exactly what that number is, but we do have the function itself. We could determine what f of negative 4 is. That's negative 4 cubed, which is negative 64. Handwritten typo. That's negative 64. And f of 4 is positive 4 cubed, which is positive 64 right there. So that's how the range would go. It would go from, so this is negative 4 comma negative 64, and this is positive 4 comma positive 64. So the range, it's the set of all y values such that y is between negative 64 and positive 64. And by the way, you may or may not have noticed that they had square brackets here. So that means that we do include the negative 4, which means we're also going to include the negative 64. And we could also write that in interval notation here from negative 64 to positive 64. My apologies once again. I'm pretty rusty having my picture and stuff here, so my apologies if I'm cutting out some things that I write as I'm talking. All right, part C, graph the function with the restricted domain. Oh, okay. So it's kind of already graphed, but let's do it again. So if negative 4 is negative 64 was, I don't know, it was negative 75, negative 64. It was about right there. So negative 64, positive 64. You know, if you start to get really good at the graphs, you kind of know what's going on, but this is a cubic function that it kind of has a little bit of that going. But it does stop, it does have closed circles, and we are finished there. That is the new graph with the restricted domain. Not perfect, but it's there. Last one, number 15, represent real-world situations. Some more stuff. The John James Audubon Bridge is a cable-stayed bridge in Louisiana that opened in 2011. The height from the bridge deck to the top of the tower where a particular cable is anchored is about, did you understand anything you're reading? It's about 500 feet, and the length of that cable is about 1,200 feet. Oh. Draw the cable on a coordinate plane, letting the x-axis represent the bridge deck and the y-axis represent the tower. Only use positive values of x and y. Write a linear function whose graph models the cable. Identify domain and range. When I said oh, it's because when they say the cable is 1,200 feet, the cable is not the distance from the tower. The cable is not this right here. The cable is this right here. So that's got to be 1,200. And I'm kind of surprised that they put that. I would have imagined it would. It's me knowing math. I would have imagined they would have said 1,300 feet here. I don't think they'd have a lot of fun doing this. Let me pause this video and see if they rewrote a version of this later to make it say 1300 instead of 1200. I'm kind of surprised here. Give me one moment. Okay, so I checked and they kept it as 1200, which, listen, I'll be honest, it makes it a daunting problem as far as what all is going on. I'm going to change it. I know there's some people that are probably looking for an actual solution thing, but it defeats the purpose of what it is that you're actually trying to learn here by going above and beyond. And you can argue that with your teacher, I guess, if you want to. We're going to follow the same things to do, but my numbers will be a lot cleaner if I change this to a 1300. I'll just let you know right now. Because the cable is this thing here, okay? Just make sure that you know that. That right there. I should really move my picture. All this white space is not being used. Give me a second. I should really not have myself. Why am I here? All right. Here we go. Cable saver opened in 2011. The height for, okay, so the 2011 doesn't matter because time is not a factor, right? Time is not of the essence here. So we are a 500-foot cable. Excuse me. It's 500 feet in the air. And it's 1,200 feet long, hitting the ground. It hits the ground 1,200 feet away. So the question is, or 1,200 feet long. The question is, how far away from the tower is that? Excuse me, 1,300 feet. How far away from the tower is that if it's a 1,300-foot long cable? So what you want to imagine here, guys, is it really is a right triangle, if you will. The cable is 1,300 as I changed it. This is 500 right here, and we don't know this length right there. So what you want to do in a right triangle is use Pythagorean Theorem, a squared plus b squared equals c squared, to figure it out. Now, this was me kind of knowing my answer stuff beforehand. That's why I said I would have preferred that everything worked the way that it did. I think it's, geez, that large number. I'm good thing I kind of know the numbers beyond that. So 14400. I don't know, what is that, millions? 1,440,000. So x is going to be, this is actually going to be 1,200 right here when you take the square root of that. So take the square root of both sides and we get 1,200 feet. So this x, this is 1,200 feet right there. That's as far as this thing goes, Pythagorean Theorem. So this cable, as a drawing, looks like this. This is me reinventing the problem. You have to remember that. This is me changing it. This is 1,300 feet. This is 500 feet. And this is 1,200 feet. It is actually hitting the point 1,200, 0. And this is 0, 500. Once again, you can use Pythagorean. If you're going to change, keep the problem as it was, the 1,200 there, you're just not going to get an integer value, and it's going to be a little bit different because they want us to write the linear function and everything else as well. I like the fact that I can go down 500 and over 1,200 and work that out instead of the decimal stuff that they actually want. It's, again, defeating the purpose of the problem to go above and beyond with that stuff. So draw the cable, letting write a linear function. So my next thing here, my slope, guys, it's negative 500 over 1,200, which is also negative 5/12. I like the fraction now that I did it. And the y-intercept here is 500. So my equation here will be, let's see, write a linear function, will be y equals negative 5/12 x plus 500. Okay, that's my equation. Now write this identify domain and range, set notation, interval notation. So set notation is going from 0 to 1,200. Oh my gosh. Very rusty in doing these videos, guys. My bad. And the range goes from 0 to 500. There you go. The domain and range of the interval notation, sorry about that, goes from 0 to 1,200 and 0 to 500 respectively. All right, that's it, guys. I believe I covered everything there. So that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for tuning in. I hope that some of my little hiccups along the way weren't too disastrous. Hopefully you learned a thing or two. Thank you so much for watching. Take care.